All right, here's our next project. A pair of fiery flame linears, phase linear amplifiers. A Model 700 Series 2 and a Model 400 Series 2. And they have the, what do they call that, the Night Rider, or the Cylon, or whatever they call those things. The little LEDs that go back and forth. So it doesn't have the jiggly meters that all of you like, but at least they have meters. So essentially what these are is a gigantic transformer that you connect to your Sirwin Vegas, and then it's a party. Literally, look, it's what it is. Transformers, heat sinks, yes, here's my hand, here is the transformer. And it wasn't easy humping this thing up onto the bench. They weigh a ton. But in all seriousness, I'm talking to Dave. We're kind of brainstorming what we want to do. Right now, our inclination is to go ahead and put the upgrade boards. Now, any of you who know what these are already will know what I'm talking about. For those of you who don't, this is an early design of this type of amplifier, and it is actually kind of groundbreaking in its time. A lot of the classic audio amplifiers that you see come across my bench are using similar designs, to what these have in them. Now, the earlier models of these used what's called a quasi-complementary output, and at some point in time they switched over to a full complementary, which means a PNP and NPN output pair of transistors. So we'll look in these and see what they are. I have a feeling these are both the push-pull or the full complementary versions, but that's okay. And what I think we're going to do is we are going to put some upgraded circuit boards. These are very famous, these are very popular. And some of the early designs of these, they had a tendency that if a transistor would short or something like that, they would really burn up pretty bad, and they can damage your speakers and a lot of things like that. The upgraded circuit boards try to deal with some of those problems, and they also improve on the performance of these amplifiers, which already was pretty fantastic for what they were. You look at the gigantic power supplies that they have to start with. You look at the huge heat sinks to be able to deal with very high power. When they're calling these a 400 and a 700, it's because these things, this smaller one can do 200 watts per channel into 8 ohms all day long. This one can do 350 watts per channel. And that's not like your little cheap hold in the palm of your hand Class D amplifier you buy for 40 bucks on eBay. These are the real deal. So I think it's going to be an exciting series. It's going to be a lot of fun. And if you all are very good little boys and girls, I might even have the matching preamp to go with it. And we'll end the series with that one. So if that sounds interesting to you, well, stay tuned, because I'm sure this is going to take some parts to do it. And should be a lot of fun. Okay, we're going to start out with the Model 400 because it's lighter weight, and then that way, as I do my weightlifting on this thing throughout this series, I'll kind of build up the muscles, and then that way I'll be prepared for the 700, which is even heavier, as you could see. Yeah, these transformers these things are pretty heavy for what they are. Pretty impressive. We're just going to see if the thing works. Now, before I plug it in, because this one does not have a power switch, the other one does, I'm going to take this top cover off, because I want to make sure that in transport nothing fell down in there, nothing shorted, nothing like that, because this power supply is no joke, and when it shorts out, it will take out everything in its path. So I don't want that to happen. I want this to be as least amount of damaged goods as possible. Okay, let's start out by checking these fuses. That'll give us a good indication if usually if these are obliterated and they're nuked, then you have shorted outputs. But there's one, and they're saying this is supposed to be a 10 amp fuse, and this is a 10 amp fuse, and it is in very good condition. I don't think I even need to measure that one. That's a good sign. Always start out before you power something up by looking at the fuses. You want to make sure that you don't have something, that was a good fuse until I destroyed it. So we will need a new 8 amp fuse, but it wasn't blown. Let's see what this one looks like. Here's another one. That one's jammed in there really bad too. And that's a good one too. AGX, I don't know if I have any AGX fuses left. I used to have them, but I may have to order one. That may have just cost me there. But you can see how that's jammed down in there. I probably should have measured it with the meter, as most of you are probably screaming at the computer. Or, yeah. So, yeah, I just broke that. All right, let me see what I have. Well, the biggest AGX type fuse I have are AGX 2s. So I am going to have to order some more. Okay, so one quick thing here. I did get my fuses in, replaced that one that I broke. Great. And I did a video in the middle of this that I posted earlier here in the middle of this video talking about the different types of fuses, and I just wanted to compare what would be the difference if we used a type AGC, which is your just standard run-of-the-mill fuse, versus these. And there's absolutely almost no difference. So if you look at the specs on this fuse right here, this is the original AGX, which is a 1/4 inch by 1 inch. And you can see the rated current. There's two that fall within the range, because anything that's, these are 8 amp fuses. So for the 1/10 to 30 amp fuses, you can operate it at 110% of its amp rating for 4 hours minimum. So yes, you can actually exceed 8 amps by 10% for over 4 hours before the fuse will fail. And you can run it at 200%, so 16 amps, and it'll take 2 minutes for it to blow. So fuses don't blow very quickly unless you have a really hard short. The other thing that we're going to talk about is the AGX 8 fuses are literally all rated at 250 volt fuses. However, the ones that I got, some of them said 32 volts on them, some of them said 250 volts. What's up with that? Well, I think it doesn't matter. They're all 32 or 250 volt if you go by the spec sheet from Bussmann. And the main difference is when rating it at 250 volts, your amperage rating, your interrupting rating, your maximum break current is 200 amps at 250 volts. You see that? 125 volts, it goes up to 10,000 amps. So that's kind of a sweet spot where it has the fastest reaction and the best protection. But when you get down to 32 volts, it's not as good with overcurrent. It's actually rated at 1,000 amps. What does all that mean? Well, it just goes to show that volts and amps work together, and how they work on that filament. You can see it right here. The other thing I found interesting was the resistance. So DC cold resistance of the actual filament of the fuse itself. For an 8 amp fuse, it's going to be anywhere between 8 and 11 milliohms. So it's really small. But look, just by moving from there up to here, it changes by 2 whole amps. See that? So a 10 amp fuse just only has very slightly lower resistance. And you can see as you go down the line, doesn't take a very big difference in the resistive value of that fuse to make a big difference in its breaking current, or in its failure rating. I thought that was interesting. Now, comparing that to the AGC 8 amp fuse, again, this one's 100% instead of 110%, 4 hours minimum. And 200% is 2 minutes, the same thing. So it's essentially the same rating. And if you go to the AGC 8R, just means ROHS certified. It's a certified fuse. 8 amp, same thing. 200 amps at 250 volts. See that? 10,000 amps at 125 and 1,000 amps at 32 volts. DC cold resistance, very similar, 9 milliohms. So this one doesn't give you a range of it, but there you go. So you could use either fuse, I guess is what I'm saying. Now let's get on to some of this. So the first thing you'll find if you go search online for the schematics is that they are complete and there's a lot of information out there, but they're not very good and they're not a complete schematic like this. So what I did was I took the individual circuits that are on individual pages and I kind of cut them out and I digitally spliced them together. So we have the big picture of what this amp really looks like. Now this is not the earliest version. The first generation of these, this is series 2. The first one, instead of having an op amp here, it has a traditional differential pair. So it just has 2 transistors in a long tail pair format. So there's a couple things different in the front end here, but essentially it's doing the same thing that this is doing. It's just they're using an integrated circuit on this one. The other thing I noticed is the one that I have here shows it to be an LF356 op amp. They also have an earlier version or a later version where they use an LF351. They're very similar op amps. We use them a lot in some of the X-ray equipment. I used to keep tons of them in stock. I'm completely out of them because they're getting harder to find, especially ones that are from reputable sources that you could use in medical equipment. And the equipment that they're repairing is now getting onwards of 20 plus years old, so they're going away. So I don't have any more of these. At least I don't think I do. So I started looking around. There's really not a big difference between these. They have slightly different slew rates. The 356 has a higher bandwidth, so tells me that it'll oscillate easier. I don't know if there's any benefits to sound, but they're pretty similar. The amp that I have in front of me right now, you can see it has these, they're in metal cans. They make a metal can version. They also make the plastic case version. And I don't know, I didn't even look to see if this is a 356 or a 351 in here. Let's take a look. That is this is a 356. So these are LF356s, so the schematic that I showed you down there is the correct one. So this is the version that we have. And you're going to find out that there are several versions of this. They've changed this through its production run. This is a very simple and very good design, in my opinion. Now, if you look, I have a couple sections here that are highlighted in orange and green. I'll talk more about that later. So if you were going to teach a class on, 1970s era high fidelity amplifiers and things, this would be one of the best ones. I mean, it's a streamlined, simple design. It only has what you need in it. Yes, it is a quasi-complementary. The original one was. I'll show you some other things here because they modified this later on. And really, with the exception of this integrated circuit, you could transplant pretty much this whole circuit into a lot of different things out there. I mean, for instance, I did that series where we built that really cheap amplifier, the Booty Fab Labs. Go watch that if you get a chance. It was an interesting series. But it uses a similar kind of layout. if you look at the series I did on the Sansui 9090, not the DB, but just the standard 9090, very similar circuitry. Pretty much everybody uses this, where you have your input pair and that's for impedance matching and for your feedback. And then you get into your voltage amplification stage. You have your bias circuit, which in this case is a VBE multiplier, and in other circuits they'll just use a bunch of diodes, and so forth. You have your overload protect circuit with these two transistors and diodes. You have these pre-drivers, and then you have your Darlington driver sets where this drives the outputs, and these are ganged outputs. It's a very high powered amp, so you see there's 6 outputs in there. Very common. You see this everywhere. So this is the one that I have right now. I've determined that mine is the original quasi-complementary that has all NPN outputs. This is kind of interesting how one transistor has an extra 0.33 ohm resistor in it. At high currents, that actually will make this draw less current than these ones. But regardless, that's how they're picking off your signal for your overload protect. See that? Moving to the newer design, because there was actually an updated version. They went to an LF351. And you see these orange lines? You can see these go straight out now. And you don't have these resistors right here. See that? And down here, you don't have this network. This network is to compensate for the difference in the forward voltage drop, because one side, you have 2 voltage drops here through the base. So you have base to emitter of this driver, and then it goes to the base emitter of this driver, which goes to the base emitter of this driver. Whereas when you look at this one, you have a base emitter junction here on this side instead of this side. There is no base emitter junction here because this is a PNP driving an NPN. So your actual forward voltage drop is different. So you have to have this extra circuitry to compensate for that. And you might want to go look at my Booty Fab Labs video where I talk about this, because in that series we go into great detail why you have to have this and how it works, and we even had to modify it a little bit from the original design from China. But you can see this extra circuitry is in there for that reason. It's not in this newer version because, you getting bored yet? This is the Model 700. We're not going to look at that yet. Because on this one, you have a full complementary pair. So you can see now where you would have had an NPN here, you now have a PNP here. So all your voltage drops line up with this side now. They're just different polarity. On this side, you have the emitters in the middle. So now your emitter resistors are facing the output. On this one, the emitter resistors are on the rail, the power rail, and there's no emitter resistors here and here. You see that? See the difference? So there are a few differences in there. And because they're all up here, you don't need that second resistor on this one to have that voltage drop to measure the current for your overload protect. See that? So now they're truly matched. Whereas on this one, you see that versus these. Now, there's a lot of advantages to this because I told you about the voltage drops. Again, watch that series on the Booty Fab Labs. But this also can work very well and does. So I don't really cash these off as inferior. As long as this part is done correctly, this can be just as good of a sounding amplifier, if not better, than this. I mean, when I heard that Sansui 9090, that thing just sounds amazing. Just it's so easy on the ears to listen to that, and it's it's a quasi-complementary design like this. Moving to the Model 700, which remember we have a Model 700 we're going to do later in this series. It's all this front end part is the same. They didn't change it. They just upped the power supplies, so you have higher voltage, higher current power supply. You could tell from that gigantic transformer. And they added an extra pair of transistors. So now instead of having 3 and 3, you now have 5 and 5. Yeah, there's a lot of output transistors to handle all that extra power. So, but again, the circuit is the same. They just added more pairs there. And you can see the similarities. Now this is full complementary by the time this one came out. And there may have been a quasi-complementary version of the Model 700, but I'm not sure. Again, I'm not an expert on these. I know a little bit because of how popular they were, and I've heard them in the past, but really haven't done a ton of work with them or anything, especially since there's so many different versions of it. Okay, so that's just some interesting things there. And they talk about these output transistors, and you can pause and read this if you want. This is all downloadable too, on various places. But they're talking about some substitutes that they're using now because you can't get those XPL 909s and FPL 909s. And actually, this amp up here actually has most original transistors. Some of them are XPL 909s, some of them just say PL 909, and some of them say Motorola, and they have the Motorola number on them. And I think those might have been replaced at some point. Now with this first cover off, again, I haven't done much testing yet on this, but everything appears to be good. Those 0.33 output resistors here, these ones, the 0.33 at 2 watts. Normally you would see these, they would be like a wire wound resistor, but they actually just used standard carbon comp resistors, and you can see they're 330 milliohm resistors, and they all look perfect. There's no burn marks, there's no tarnish, they look perfect. So what I'm going to do is I have a very accurate ohm meter that uses the Kelvin leads, and let's just look at these because, of course, carbon comp resistors have a notorious reputation for drifting with age or with failing or with getting noisy. I believe these are actual Allen Bradleys, although, yeah, they probably were kind of shiny in the beginning. Yeah, so they last a pretty long time. I'm still not a big fan of putting those in a high current situation like this. But again, hooking up to there, if you look at the meter, that 0.33 is 0.34 ohms, and that's dead accurate, this meter. So you can see, and I actually went through, spoiler alert, I went through and I checked all of them this way. They're all perfect. They're in absolutely, there's no reason to replace them. They're in perfect condition. Nothing wrong with them. So I don't think this amp has ever had any big massive failures of any kind. Nothing looks burned up, nothing looks overheated, there's no hot spots on the circuit board. So either this amp was very well cared for, or perhaps it just wasn't used that much. Now I don't know if all the transistors are still good or anything. You might have some noisy transistors or something in here, but we'll check all that out later. But for right now, I don't see any reason we can't power this up. Now, of course, I'm going to put it on a current limiting bulb, but I think this thing's probably just going to turn on and work. Okay, I have my noisy, buzzy isolation transformer on, and I'm connected to my smallest current limiting bulb. And I'm just going to check and see if we have at least the B plus up here. So let's turn it on. And the light flashed, and now it's dimming, dimming, dimming. And it's settling down. Very good. So let's go from here to here. And we have 48.5 volts. And let's see if I can reach down here without shorting everything. See if I can get 48 volts here. And I do, negative 48.5. So they're balanced and they're good. Now, if there was a short somewhere, one of those would probably be closer to 0 volts. And in addition to that, that bulb would be super bright. I mean, this is the smallest bulb I have, and look how dim it is. So it's obviously not drawing excessive current, and I like that. So leads me to believe that I can probably connect my scope to this and feed a signal into it. We're going to do open circuit test first. We're not going to, and no, this is not a vacuum tube amplifier. You can run these without a load on the speaker terminals. Okay, a lot of people comment on that. But no, that you're getting confused with tube gear. You don't have a reflected impedance. You don't have that output transformer. There's none. You don't have to do that. Transistors are low impedance devices, and they don't care if they run open circuit. Okay, I have a signal generator connected to the inputs. I have this little scope connected, and I'm still on that current limiting bulb. Let's turn it on and see what it does. And I'm getting noise. Let's see. Huh. Okay. Just got to set my scope. There we go. Nice. Okay, so the first channel is passing a signal. Let's look at the other channel and see if it's passing a signal. As I disconnect my output here. Hey, it works, and actually looks pretty good. Maybe we lucked out and got a working amp on the bench for once in like 500 videos. Okay. Well, since we were able to pass a signal through this thing unloaded, and we didn't have any DC offset or anything like that, I think we can now connect a load. I'm still going to leave the bulb in there just in case, because these things are unstable and they can oscillate. And we're connected to an 8 ohm dummy load, and I have the scope connected. I have the same signal generator, same signal. I'm not going to change any of that. I do not have the signal generator on yet. And let me get this lined up for you. And we're going to check. Let's see what happens, and then I'll put a signal on. So turn on. Oh. Well, that's not good. That's really not good, is it? Okay. Okay, so I checked my scope and everything, and first of all, I have the probes input set to 10x, and my probes were switched to 1 times, so that was off. So I switched them the correct way now. Let's see what we've got now. Huh. Now it's working. I mean, it was literally, you saw how it was oscillating. What the heck happened? I don't like that. Do I have a loose connection? Let me switch these back to... No? I'm switching the probes between 1 times and 10 times. It's not making any difference. You saw what it was doing. That amp was absolutely going into crazy oscillation. Well, and the bulb is now dimmed down where it should be. It just goes to show how unstable these things can be. But, okay. Now, undoubtedly, this is not going to work too well because I'm on only like a 40-watt bulb, but I am going to turn on the signal generator. I just want to see what happens. And look at that, it goes crazy. Wow. Okay. So I have one channel, I'm getting an output, and the other channel, I am not getting an output. That's strange. So let's see if maybe we have a bad connection somewhere. Or maybe one of these, oh, I think these pots are not so good. First of all, there it is. Okay, I had a bad connection on my, so the RCA terminals are very dirty, and I think that's what's causing that. If you look here, bulb's really bright, but I definitely am getting an output. I'm getting about 18 volts RMS. So we're actually driving some power into this thing right now. So two things we figured out. Number one, let me shut this off. So we figured out two things. Number one, the connectors are dirty, the RCA input connectors. And number two, the input sensitivity potentiometers, which would be basically these fancy volume pots, are very dirty. So we just need to clean those and clean our connectors. And it looks as though this thing is working. Okay, let's see if I can do this around the camera, and I'll zoom in a little more. So here, everything's so easy to work on. This is a very, very good amplifier from a service standpoint. And they're just easy to work on. So what I'm going to use is just these brushes. You can buy these cleaning brushes on eBay type places, and they're relatively inexpensive, and they're really good for this sort of thing. And I'm using, a no residue cleaner. I'm just using this CRC cleaner here. That way, if it splashes around in there, it'll just evaporate and won't hurt anything. And this is kind of a little awkward around the camera, but I'm just going to do this so you can see. You just want to clean that up. And it should look shiny in there. There shouldn't be any tarnish or anything. Let's go do the other one. And then we'll also want to do the ground side, the outer ring. I'll do that next. Spray some of this in there as I get it all over everything, which is why I knew better than to use something that would leave a residue. Okay, and we'll just clean that out. That looks good. And then I'm just going to plug this in to just see how it seats. I want to make sure it's not real loose. And as you can see, these don't go very far up in there in a standard RCA. But it does look like it's making relatively good contact now. So the next thing I'm going to do is I'll clean the outside of it. And I can just use, of course you can use a little piece of really fine emery cloth like this. This is 1500 grit or even higher than that. Or you can just try to clean it off with the solvent, which is what I'm going to do. I'll just put a little bit on a rag here and just clean it. As long as it's not badly tarnished, and these ones aren't. They're just dirty. I think this will be, yeah, they're coming out real shiny. So this will be fine. You could see it does get some grit on it there. So I'll finish cleaning this up, and then we'll come back and we'll do the potentiometers. Okay, the pots are right up inside here. They're really easy to get to. I'm going to start out with this like I always do, and then I'll follow it up with some fader lube. And just run these back and forth. few times. They weren't terrible, but when I moved them, they did have a lot of static on them. So I think they're just dirty. They're not worn out or anything like that. They're just dirty. So these can be cleaned, and we won't have to disassemble them. They feel good, so I don't think we're going to have any big problems with that. So let's go do this one now. And then once I get this cleaned out, we'll put a little shot of fader lube, and these should be good to go. So we'll put some of the green stuff in here. This works really well. It does leave a little residue, and you just need a tiny little spray in each one. And that'll last a long time. And we'll work these in, and I think we'll be good to go. Now, if you wanted to get fancy, you could remove these pots from the chassis, disassemble them, and you can, put the damping grease in there to kind of give it that, that kind of fluid feel when you turn them. It's not necessary, but it is nice. It's a nice touch. And you can actually polish the wiper off, for the center ring and the little wiper. You can polish those. But I don't think that's going to be necessary in this case. I think there's no tarnish. I think it was just dirty. All right. Let's go back and try our luck, huh? Okay, I've connected the RCAs back up, the signal generator. I'm going to go over here, turn it on. And would you look at that? Let's take a look at this. What is this that we're seeing? The bulb is going to protect us so we can play around here and see what's going on. But you can see how bad that oscillation's back again. So let's move this connector around. I'm going to take these out. So now the connectors are totally unplugged, and it's still doing it. So now let's turn the volume pots down. And as you can see, that doesn't do anything. Okay, so I'm showing you what I'm doing here. Nothing. Isn't that strange? And look at the bulb lighting up. I mean, it's putting current into the load right now. This thing is oscillating. This channel, the right channel, is really oscillating. I'm at 50 volts per division right now. And look at that. So it's going to the rails when it's doing that. The other one is not as bad, but it's also very bad. So obviously something is either loose. I'm just tapping on the boards right now. And again, this is why you want a really small bulb in there. You don't want anything to get so hot that it's going to damage things. So I am not seeing, being that it's common to both channels, I find that a little bit curious also. So there's something in there. It's either a capacitor that's dried out, or a transistor or something. But something is causing the amp to go into oscillation. I think the right channel is the one that's the culprit, and I think that on the left channel, that smaller oscillation, I think it is actually a result of what it's doing to the power supply. And you have that gigantic that light bulb that's given that huge amount of current limit, and you're just seeing the power supply tracking it. So I think we have a problem on the right channel, even though both channels appear to be oscillating. They're oscillating at the same frequency. And so left channel, you're looking at power supply following the light bulb limiter. and the right channel, which is the blue channel, is the actual one that's oscillating. I went and I read through some of the service notes. There were some service notes. And this is the first one. I'll read this to you. Some of you probably already know this, but some of you may not. So the early Series 2 amplifiers. Okay, so we're talking about the Series 2, not the ones. They have these they have an LF, it says use a LF356 input op amp, which required relatively high supply current. Later in current productions use a LF351, requires less supply current. Because of this change in current demand, the dropping resistors R1 and R2 were changed to 7.5 kilo ohms, and they were previously 2.4. So you can see we have we have some 1.8s in there and 2.4. So if you look, these are 1.8K. So previously 2.4 kilo ohm 5 watt for the model 700 and 1.8K for the 400. So these are 1.8K. You can see it says 1.8K. And what they did is they switched this over to an LF351. Now, why did they do that? Well, I'll show you. Okay, here's a little more about this. So in the first year production runs of the models 400 and 700 Series 2, the PL36 PC driver boards, which is that, we used a TO99 packaged Fairchild or Signetics LF356 BiFAD op amp. This particular IC package was found to cause an unacceptable turn-off thump in some amplifiers. We later discovered and this is because this thing does not have a speaker protect circuit. So later discovered that when you used a production of the 8-pin mini dip package LF356, which reduced this thump. So the metal can, according to this, was the old version, which is this one. And it appears that the later version, they went to an 8-pin mini dip, which was the plastic case. And apparently that made it better. And then in May of '79, they changed it over to the LF351, which was found to have a better slew rate, lower distortion, and substantially reduced delayed turn-off thump. They are also cheaper. So it basically said if you have to replace these or you have excessive turn-off noise, go to the 351. Now, I'm out of 351s, I'm pretty sure. We used them like crazy in a couple of pieces of X-ray equipment, a whole series of them actually, from the early, late 1980s, early 1990s, clear up until the 2000s. And I've pretty much burned through my supply of them. You can still get them, but you can't buy them through places like DigiKey and Mauser. And if you got to stick with ISO certified sources and things, it's starting to get hard. But long story short, a better alternative to me would be to use a TL071. Or today, probably a TL081 would be the same, because I don't think there's any difference anymore when you order brand new ones, because I think they're the same thing. They don't change the internal components of them, just from what I'm hearing and experiencing. But anyway, TL071 would be a better thing. So what I think we're going to do is we're going to replace these with TL071s. Before we talk about the plan for fixing this, let's go back and see if we can narrow it down to the individual component. Okay, you folks know what I did. I shot this beautiful video explaining everything here, and we found something out. I found it out, and of course, I didn't have my microphone on. Yeah, went upstairs for a moment, came back down, forgot to put the mic back on, started talking, and well, yeah, another Tony thing. So let's repeat the experiment, and hopefully this thing will do the same thing. So as I was saying, I took this thing all apart, and we're going to look at kind of why this thing's oscillating a little bit more. And I got to thinking, this LF356, we read in that instructions that it requires higher current, hence the 1.8K resistors as opposed to the 7.5K resistors that are used in the 351, LM351. And I got to thinking, with this 40 watt current limiting bulb, there may not be enough voltage, incoming voltage, to suitably get our plus and minus 15 volts or something near it. If you really get down below that plus and minus 5 volt range, this really isn't going to work, and this can all become unstable, and that might be what's causing it to oscillate. So, because that's not a real world scenario that you would typically have. So what I'm going to do is I'm going to see if we can repeat this. Because what I found is that's in fact what it was. So we'll turn this on, and there it goes. You see how it's oscillating right now? You can see how bright the light is. And I can randomly turn it on and off, and eventually it'll clear itself. So we're right on the edge of working and not working. But let's add another 100 watt bulb to increase the current and raise the voltage here. And as soon as I do that, it settles right down. So I think the oscillation is not going to be a problem. It's literally just something that has to do with we were starving it for voltage. That's good. So we're going to continue on now with our evaluation. Now another thing that can cause oscillation in here, if you read that, let's go back to that note we were looking at. Let's see where I was. Here it is. Another thing they're talking about is the output transistor insulators. Some of these use sill pads, apparently. They used sill pads, and there's a possibility that you can get parasitic oscillations. Now that's not what we were seeing. A parasitic oscillation would be if we put our sine wave on there and you see these little blips, along that sine wave trace. That would be parasitic oscillation. We're not getting that, but this is definitely something we want to look into. You see that? And the other thing is voltage at line plug, they want 120 volts. So right there's another thing. If it's at low frequency, we were at low test frequencies. That was a low frequency oscillation. So again, it's because we weren't at 120 volts. When I added that other 100 watt bulb, that was able to get the voltage up high enough to get beyond that oscillation area. I still don't like that. This amp should be stable down below 120 volts in a perfect world. So we're going to try to do things to help that. So now let's also talk about some improvements that we could make on this. Number one, the output transistors are all originals, and you'll see when I take the cover off later on that one or two may have been replaced somewhere along the line, but definitely they're old. So one upgrade could be to upgrade those to modern transistors like the MJ series. Would they suggest the 21194 or something like that? I can look it up. There's a lot of different options we could go with on those, and they'll work. The other thing would be to go from the LF356 to a TL071. The TL071 or the TL081, both of those would be good. They used to be different quality op amps, but the modern ones that are made by TI, I don't think there's going to be any difference between a TL081 and a TL071 other than the numbers. I think they come off the same production line, and they might grade them, they might not, but they're basically the same. But anyway, TL071s to replace these. We can leave these transistors alone for right now because I'm sure they're going to be okay. These capacitors are good, but they're old. So, well, I'm assuming they're good, but maybe they're leaky. But there's 4 of them. very inexpensive to replace them, we'll do that. These resistors will need to be changed to a larger resistor. We're going to have to put in a set of, what is it, would they say 7.5K? Where's the little note again? Right here. Change to a 7.5K at 5 watt. So we'll have to do that. But what I might do in place of that to get rid of all that excess heat is I may just install a set of constant current source boards. You've seen me use these before. We can modify a couple of the values on the little board and we can calculate what this current should be, and we'll be able to get the correct current, and those current sources will run very cool and they'll last forever. We won't have to deal with it anymore. So I'm going to do a few things like that, and then we're going to test this amp out and see how it performs. So I'm going to end this part right here. And what I'm going to do is I'll get it uploaded, and in part 2, we will actually replace the op amps, install the constant current sources, replace the capacitors, check all of the components and make sure they're good. If everything's good in here, we'll leave them as is, and then we'll give this thing another test and see how well it performs. So until then, and probably we'll replace these capacitors. I may just go with the same type that's in here. I don't, of course, not Sangamo, but there are modern, I think, Cornell Doubliers that the same cap I could replace. There's also a little better quality ones that I could put in here, but we may have to make a little adapter board or something. Now, I know a lot of you are probably going to ask me about those Oak Island boards, or yeah, whatever they are, the oak boards. I'm probably going to, at some point in time, try that. I was talking to Dave about it, but I think we're going to save those for the Model 700. This one I'm going to try to keep pretty faithful to the original design, but put in the modifications. I'm not going to convert this yet, at least at this moment, to a full complementary design, because I kind of like the quasi-complementary. You know, to get a tiny little bump in distortion figures and so forth, I don't think it's really worth it to me, but I don't know. So I'll probably leave those alone. And that's about it. So again, until next time, I wish you all peace, joy, happiness, and good health in your lives. And when we come back, we'll be getting away from the schematic things and getting into the soldering things. So those of you who like that, stay tuned, because we'll be doing that. Take care, everybody. Bye-bye.